Okay, how's everyone doing? You're getting close. You're getting so close. Today is this day, 17th. That's 1 week. That's 2 weeks. That's 3 weeks. We have 3 weeks of additional learning. And then we're going to present. Okay. Now, there is a finals time for this class, which we can use. Or, depending on people's conflicts with other classes, we could just use the normal time. So I would prefer if you have a look at when your finals are, and you let me know which of those 2 time periods we should use. Ideally, the way that it'll go is you'll get like 10 to 15 minutes. Ideally, you present for 7, you take questions. It'll take some amount of time to switch between speakers, okay? If you haven't looked at or even begun to think about your final project, I'm gonna get you. We can talk about it, send me messages, find me in the hall, come to office hours. Really, you should be thinking about it now. It's not a significant more amount of work. It's a 1.5 homework problems, but I'm hoping that you're all catching up to your homeworks. And in doing so, you're like, wow, I really have the tools to do this on my own. Part of what your final grade will be is, do I think you could code on your own? If the answer to that is no, you're looking at a C or below. Okay? If you can't write code by the end of 15 weeks, you have not learned computational physics. You've learned physics, but you haven't learned computation. Okay? Questions, comments, concerns? Okay, we didn't really finish that conversation about eigenvalues, but I think people were close, hopefully. We were building the H matrix. We had a double for loop. We had an if statement. We figured out if you do the if statement in reverse and you ask if m is equal to n, that's the best way to start. And then you have an else if statement that checks whether or not they're both even or both odd, right? And then you finally have, else, and that would get all 3 of them. So if you check them in reverse order, it's the easiest way to write that code. And so you fill out all of the things into a matrix, and then you just use linear algebra to solve it. Generally speaking, it's good to know how to do this, okay? Knowing how to use projects, knowing how to set up code, even when you have no idea what the physics is telling you, right? So you don't have to be a master of quantum mechanics in order to do that problem. Okay. So now we're going to kind of shift gears. We're going to talk about nonlinear equations. Eduardo is happy about this because he already told me it's a fucking lot easier. Okay, so I hope you're reading ahead and you also know that this will not be as bad a class as some of the others have been. Then Zori will tell us about how to find maximum and minimum in a graph computationally. That's important to do, right? When is my money at an all-time low? Right? When is my money at an all-time high? Hey, yo, all right? Okay, and then we'll shift gears again. Alfred will begin to tell us how we take integrals. What's the definition of an integral in English?
A sum.
A sum of?
Individual arbitrary properties
Of?
of some graph.
So that would be a sum. What is it? What integral's got like a special meaning, you know? Like when we talk about like the derivative of a function, it's the good. And so the integral is the
Overall change. The area of the curve.
bingo. So that's something we want to hold on to. Because when we go into section 5, keep that in the back of your mind, right? You're going to make graphs, you're going to make pictures, and your job, like Alfred was saying, is to count up all of those slivers, and you add them all up, and if you make the slivers small enough, they approximate the area under the curve, right? So that's where we're headed. We're going to take the idea from Eduardo, we're going to take the idea from Alfred, we're going to hold those in our mind as we read those chapters, okay? We'll talk about number of steps. We won't get very far in understanding integrals. That's because integrals, honestly, kind of boring. You can take integrals with Wolfram Alpha. I think there's a lot of value in knowing how to do it, but you don't need to do it. You don't even need to build them from scratch anymore, right? It's like, it's important to understand how to do an exponential or how to take a square root, but I'm not going to teach you how to like look it up in one of these books, right? You can just type it into your calculator. Okay. We'll probably end with random numbers and using what you learned. That'll be just a conversation about how we create randomness on a computer. Is there an ability to create a random number on a computer? A truly random number?
No.
No. Why?
When I first took my first computer science course like 5 years ago, I needed a random number for my part, and I went through hell trying to get a good random number. But basically, any sort of data that a program produces is based off data that it is holding. So if you ask it for a random value, it's going to be ultimately based off some finite data that it has.
Correct. So random numbers do exist in nature, and we can find them, but they don't exist on a piece of hardware, to Alfred's point, which has zeros and ones in fixed locations. So if you have zeros and ones in fixed locations, then if you have an algorithm to generate a number, always work out what that algorithm was, right? So we will approximate randomness, okay? There is a metaphysical or a philosophical question, which I invite you to spend the next 3 weeks thinking about. Does your brain have the ability to create a random thought? I'll let you think about that one. Because that has, yes, it does not have the ability to create a random thought. So there is no such thing as free will. All neurologists will tell you this. And as you begin to understand quantum mechanics more, you'll become more convinced that in fact, we have never had a novel thought in our lives, which sucks. Okay. The implications for that are more moralistic than anything else. You know, thinking about how we punish crime in the United States is something that you should reconsider if you imagine for a moment that no one has ever had a novel thought in their lives. But that's way outside the purview of this course. So we won't talk about that ever again, unless you come into office hours. We're almost done. Anyone feeling like they want to quit school? I do. I want to just quit as a professor. So I can imagine what you're going through, right? Because you have a lot more pressure. So, you know, I really want to make sure that as we sort of run out of steam here, I mean, 15 weeks is a long time. You know, when I did my undergrad, I did 10 weeks and that felt like it was too short, but there's no 13-week school that I found. That's like the ideal amount of school, right? 10 weeks is too short because you have an exam every 3 weeks. You lose your mind. And then 15 weeks just feels like a slog. You're just on and on and on and on. So I want to make sure that the material that we learned at the very beginning, we're not forgetting it. You know, so if I ask you to do something like look up where splicing comes from, or if I ask you to pull out a piece of paper and to write your map of how you're going to attack this problem, or loops you're going to use, if statements, all I'm trying to do is I'm trying to tie back into what we already know, so that we're not trying to learn everything brand new in week 12. Okay. Okay. Questions, comments, concerns? Right after we finish this, I encourage you to go to Canvas. There are things called SOTIs available. Fill them out. Tell the university you hate me. Tell the university you love me. Do whatever you want. They are anonymous. They are actually used. I like to read them. They help me make the class better in the future. You know, this is an experiment with the ungrading thing. I think there is mixed results here. Some people are doing really well under it. Some people are doing really poorly. And so if you can tell me a little bit about your personal feelings about how the class is laid out, whether you would have wished to have seen more material in this respect and less material about this, that's how I can make this class better. I mean, not necessarily for you, I apologize, but for others, right? Okay. Okay, Eduardo, let's talk about nonlinear equations. Oops, fuck, I was showing someone input output. Oh, it's right there. Hey, yo. Right, this is it.
Yeah.
6-3. All right.
To begin, is like to reflect back on the linear equation. Saying like, when we were dealing with linear equations, how there's like no exponentials in the equation. So with that, there are techniques that we were using, but in this here, it says that there's no real technique to for solutions in nonlinear equations. The nonlinear equations have
Let's pause for 1 second. What is a nonlinear equation? Like an example? I'm just gonna write them on the board. Anyone can shout here. Like, give me some y equals x squared, okay? Y equals x squared. That would be nonlinear. Anything else? Y equals sine. That's definitely nonlinear. Logarithms, we hate those, right? ln of x equals 4 plus x. Anything else? What about x equals 2 minus e to the minus x? Can you solve that? Can you solve that?
With a good guess.
With a good guess? Okay, I like that confidence. What about this one? That one I can solve. What about this one? That was a little bit of a barf, right? What about this one? You don't like that one? Could definitely solve that one. That's still a parabola, right? Okay, this one you can solve. This one looks gross. This one looks horrifying. This one looks bad. Okay. These are all versions of nonlinear equations. And they're not always obvious, right? Alfred's said if he guessed, he could maybe get it. And so now we're going to learn how to guess. Okay. Go ahead, Eduardo.
Yeah, that's what we're saying, like, if we're dealing with equations that are not lines anymore, so that makes a huge difference in how we approach these. So this technique, the relaxation method is used for a single variable case. So we have an example, x equals 2 minus e to the negative x. It says there that there is no known analytical method for solving this equation. So we have to turn to a computational method, which means that you just plug in a number, you will start out a number, and then we continue iterating, replacing the number to get closer to the root number that gives us the true value or the solution to the equation. And then so we're using that equation as an example. So we see a little bit more down. And then we have the equation being solved where x, the dash, the x prime is like the second iteration being done. Then the third, and then we have the computational physics there, related code. Straightforward.
Yeah, can you explain this to us?
So you're essentially putting the equation into a for loop, starting at an initial value of x. You choose you chosen x is 1, and then for k in range is 10. So we're just going to go from we iterate the program 10 times.
Okay, now do I use the information k anyway? Do I like add that into the equation? Good. It's not shown anywhere else, right? It's just a timer. Just says I did this once, twice, 3. Okay. And now what happens?
And then out after and out X, once it calculates X1 with the next time and it redefines, then you have to print out at X where you would see it getting closer to a value. It gets closer to the value that would be
Good.
the solution to this equation.
You see that? So first it starts at 1.63, then it goes up to 1.8, then it goes up to 1.83, then it goes up to 1.840, and then it goes up to 1.41, and so on and so forth until you see that the difference here between these two is in the 1, 2, 3, 4, 5, 6, 7th decimal place. So that's a number that's good to at least 6 decimal places, right?
So this is what's called like it's converging to a solution for the problem, which is a fixed point. And so this is essentially the relaxation method, which is but finding roots to the equations by putting in numbers. And so this method does have its problems.
Let's see if we can define a few of those words really quickly. What do you mean by root? It's an answer, yeah. A root is another word here for finding the place where this thing is true. A fixed point here is the fact that we're sampling a lot of space. And because this is an iterative, you do it over and over, it iterates, it'll head in a certain direction. Now that fixed point could be local. You could find that it only encompasses this region. It takes these answers and funnels them towards it. Or it could be global and it could take all answers. But you could have multiple fixed points. And sometimes if you start too close to one fixed point, you don't find the true fixed point, which is over here, right? Okay, let's continue.
It points out some of the problems that the equation has. It says one of the things is that the equations have to be in a simple form, x equals f of x. So if they give you like a huge target with all the values on the left and on the right, you have to like solve it out.
Good.
So that's one of the problems it has. So if you get in a very since it's a non-linear equations we're dealing with, we're going to see some crazy ones, and so it will be difficult to rearrange it to look like how we wanted to compute it. But it's still possible to get x by x.
Yeah, let's ask this question really quickly here. Can anyone solve this equation? That seems too difficult, right? That's x equals e to the 1 minus x squared. Is it solvable? Alfred said he's a good guesser, right? Had a good guess. 1. What'll that do? This is 1 minus 1, which is 0, and e to the 0 is, and x is, oh shit. Okay, so if we do a really good guess, we could get it. Let's see how the computer does. Go ahead.
Before we get into that, there's the second problem for these equations is that sometimes we have multiple solutions to the equation, and so it may not be we may have problems trying to locate the different solutions when there's multiple. Because it doesn't always convert. It will convert to a single one, not to two different ones. So we'll go ahead and so the program, after it's being iterated, will give us those values.
Bummer, right?
And so if you see it doesn't truly converge into a fixed point. So we see that there's no, so it's telling us that there's no true value. There's no solution to the problem. But clearly we see that there is one. So it's like, okay, so what's going on here? We know that there is, but it's saying that there's. So sometimes another problem that sometimes you have to rearrange the solution or the equation so that it could be. We just have to it says to change the way the equation looks so that we could try a different equation, but it's still the same. equation.
Yeah. Does that make sense what he's trying to say then? So we're rearranging it algebraically. It's the same equation, but just so that it doesn't have some of the properties, right? And we can talk about what those properties are if you're interested in, say, math methods too. In this particular circumstance, back to Eduardo's point about multiple converging points, that's going to be one of the first things you do in the pair programming today, is to fit a very large polynomial. And by trying to find the roots, the places in which you have these minima and maxima, you will necessarily, you'll have to pick very carefully your starting points. Okay. Continue.
So the equation that we saw earlier, the one on the board, they rewrote it by the laws. So mathematically, it's like that when it's rewritten. It's still the same equation that we written. It's equal to square root of 1 minus log x. So they ran the relaxation method using that form, and with the starting positions of x is 1/2. And then you'll see that the values are getting closer and closer to 1.
Cool.
It gives us like the mathematical theory behind why the relaxation explains why this works, why rearranging it works. So it kind of goes through like this Taylor series, rearranging the forms. Essentially, you'll find that it's the derivative of the function. That if the derivative of the function is greater than 2, then we know that because it's an exponential, the value would kind of be thrown off and not give you a solution. But if it's less than 1, the solution would start getting closer and closer to the solution. Because remember, we're dealing with nonlinear equations. And so it's based on exponentials. And so if it's less than 1, when it's exponentiated, the value of less than 1, it's going to get closer and closer to 0. So that tells us that it's going to go into a root or a solution.
So I'll just add one clarifying statement there, right? So like exactly like Eduardo was saying, here we have the difference between 2 adjacent guesses is proportional to the 2 different guesses times the derivative. For this particular problem, we are using exponentials, but it's not necessarily the case that every derivative will be an exponential, right? Okay, so if they're less complicated, like this one up here, then the derivative obviously will be easier. But in this particular case, when the derivative is an exponential, and just like you're saying, it blows up very easily, then we don't want our next guess flying away so quickly, right?
Which is also good for us, because that means that the root or what we're trying to look for the fixed point, it'll reach there, it will go there faster than usual, rather than a linear you'll see like a linear progress, you'll see it go there. It's not linear.
Okay, so let's we don't really need to talk about the rate of convergence. We're gonna play with this. Do you want to talk about this example at all? Did you get this far? Okay. Do we know what ferromagnetism means? Yeah, this will be ferromagnetism, which is related to ferroelectricity. You know what this means?
Like iron,
Yeah,
magnetism.
yeah, kind of magnets. Magnetic dipoles that occur in a material due to the rotation of the things inside of the atom. Right? So you have current loops, and those current loops, specifically the electron moving around, appears like a little loop of current and creates a magnetic dipole. And those magnetic dipoles all point in the same direction, like in a metallic structure like iron. And so iron is magnetic. Now, it doesn't start off magnetic, it doesn't come out of the ground magnetic, but it can be made to be magnetic by changing and lowering the temperature or by orienting it within a magnetic field. Does that make sense? Okay. So this is the idea of the strength of the magnetization is due to the magnetic moment, how strong those intermolecular magnetic moments are. Tangent, hypertangent, I should say. J is some constant. M is the strength of the magnetic dipole. So here's the nonlinearity. The thing we want to solve for, M, is equal to M, right? And it's inversely proportional to something which is KT. What does KT mean when you see KT together? Energy. So JM is an energy on the top and KT is an energy on the bottom, right? So basically what this is saying is what's the energy in the magnetic dipole compared to the energy in the bath in which it's living. Now, I say bath, but I mean just like the heat environment in which it's living. It's much hotter. It'll be easier to change the magnetic dipole, right? We get that? Am I lying? I'm talking, so I might be lying. Okay. Cool. You want to walk us through this problem?
What they can find.
I mean, if did you want to do this example or? Okay. Okay, so I'll just pick up from here and we'll talk about how we go about solving a complicated issue like this. So let's say we have some things, we have some C and we have some T. We want to solve for M. And maybe we want to even vary T back and forth, heat it up and cool it down and see how the magnetic dipole changes as a function of temperature, right? So I can't just guess that. So I need the computer, right? Let's see if I can do it. Here's math. There's my hyperbolic tangent. I'll also need my hyperbolic cosine. Lin space, I'm going to plot shit as well. There's my maximum temperature. I'm going to do this for 1,000 points, and I'm going to hope to get a really good accuracy. Okay. My y, as I show you up here, is going to be description of this. The Lin space is going to go between the maximum temperature and the number of points I have. So I'll start at 0.01 points and go up to 2 degrees or whatever it is in the 1,000 steps. And then I'm going to loop. I'm going to go through each one of the individual steps in temperature. Okay. And I'm going to say, I'm going to start with the magnetic dipole moment equal to 1. I'm going to start with a huge error. And I'm going to ask to solve this with relaxation. So what I'll do is I'll just start on the right-hand side. I'll put in this information for C. I'll put in a guess for M and whatever my T is for that specific example. And it's going to spit out a new guess for M. And then all I'm going to do is I'm going to compare the new M to the old M. And when the difference between them is like 10 to the minus 6, I'm like, cool, that's close enough. Let's move on to the next temperature. Then I re-guess this at 1, and I keep iterating down until I get a small enough uncertainty. Does that make sense? Is this process weird? We've seen it before? You've never seen it before? You've seen it when you had your phi and your phi prime, and you update your phi prime with your old values, and then you swap them, and all you're doing is comparing, when you take the difference between them, is there any small numbers, right? Are they all small numbers at small changes? That's the same thing you're doing here, but you're only doing it for one number. So instead of comparing the entire array, you're comparing one number, and then you're updating that value, updating that value, updating that value, updating that value, until it stops updating. Okay? So let's look at it here. I have M1 and M2. Oh, that's interesting. Here's my M1 that's equal to my old value. And then my new value is equal to my old value. Awesome, right? It's exactly the same. And then what I need to do is I need to remember both of them. So I keep an M1 and an M2. And that allows me to take the difference between them and make sure that my error is not larger than some value. You'll notice here that I'm doing a couple extra things. This is not only the absolute value of the difference between them, but it's the absolute value of the difference between them divided by the derivative, or I think it's 1 over the derivative, right? So you do that in order to make sure that the difference between them is on the same scale as the answer is supposed to be. Does that make sense? You can delete that if you want in future work. If you don't want to calculate it, you just want a number to a certain accuracy, but you'll need to adjust that accuracy so that it's appropriate for your work. Okay, and then once I have an answer that I'm happy with, the loop ends here, and I just append the new answer into my list, and I move on back to the beginning of the for loop, and I do it again. Now I'm going to plot all the temps that I just went through and all of the answers that I just got. And what do we think we should see? A smooth curve, right? How does it look? It's going to start over here at low magnetization and low temperature. And it's going to do what? Like this, or like this, or like this. We don't know, right? We don't have a good guess. Well, it looks like that. Ooh. What the heck? So it starts fully magnetized. And then as you heat it up, what does it do? What? Okay, so it's fully magnetized at low temperature. As you heat it up, it decreases in magnetization. So you have some really nice magnet that you bought online and you leave it next to the campfire and you go to use it later in the day and it doesn't stick to anything. Bummer. Okay. That is magnetization model. Does that make sense? Okay. Okay, so let's try this. Here's nonlinear. Where's the pair exercise for today? I believe this is still the right pair exercise, but I might be wrong. I often am. Where is it? Oh, there's 611. What did I say? 610. 610 star. Aha, here we go. I'm so smart. Okay, so let's try this problem out. Let's find a friend, pair up with them, ideally someone new that you haven't worked with before. We know that that might be impossible at week 12, week 13 that we're at. Here's this equation that we're going to figure out. And we're going to write a program to solve for the relaxation method for the case of C equals 2. I would encourage you to start with the example. Okay. And then we're going to make a plot of all of these different values of C, and we're going to show how that changes. Okay.